taking the time to join us today for this exciting webinar brought to you by Syntica. My name is Kara, and I'll be your host for today's webinar. Our webinar today is entitled Gamma-I Calibration, System Characterization, and In Vivo Imaging of Actinium-225. Today's webinar will be given by Dr. Caitlin McCutcheon and Dr. Jacob Hesterman. Caitlin is a Senior Research Associate in the Translational Pharmacology Group at Ratio Therapeutics in Boston, Massachusetts. Jacob is the Chief Data Officer at Ratio Therapeutics. He has almost 20 years of experience in nuclear medicine imaging hardware, reconstruction, software, image processing, as well as quantification. Before we begin, I'd like to briefly mention a few housekeeping items. We anticipate that the presentation will be about 45 minutes, which should leave us with some time for questions. Please submit your questions in the Q&A dialog box throughout the presentation, and we'll review them at the end. We will also create a transcript of the questions we answer throughout the session, as well as those we may not have a chance to address. This transcript will then be made available afterwards. So please note that we are also recording today's session, so if for some reason you lose connection or are unable to hear, you will have access to the video file to review later. Without further ado, I'm pleased to turn this over to Dr. Jacob Hesterman for today's webinar.
Great, thank you very much. We're excited to present today. So let me just advance to the next slide.
So before we start the webinar, we would like to ask a couple of questions of the audience in order to understand a little bit about the work that you're doing. So we have 4 poll questions. The first is, what are you hoping to learn from this webinar? What types of technologies or isotopes are you currently using? What is the focus of your work? And are you currently using alpha-emitters in your work? If you could go ahead and fill in those answers, that would be greatly appreciated. We'll go ahead and give you about another 30 seconds to answer if you haven't had time yet. Great, thank you all for sharing some time to tell us a little bit about yourselves. Now I'd like to return things to Dr. Hesterman.
Perfect, thank you. All right. So a little background first, just to set up the talk. So we're going to be talking about some work with the Gamma-I, which is a planar imaging camera that we can use for in vivo assessment of gamma-emitting radioligands in mice. And we're focusing now, I think if you're joining this, we all know that radiopharmaceutical therapy with alpha-emitters is active area in drug development discovery. We also know that imaging alpha particles is tricky. We have to rely on gamma emissions that are typically coming from daughter decays and often not in high abundance. And then also if we want to reflect reality, we need to keep our administered activities quite low for this imaging. So it can be tough. The purpose here was to look into what we could do with a newly available collimator for the Gamma-I. And so we're going to talk a little bit about some of the calibration and characterization steps that were taken. I'll introduce that work briefly, and then hand it over to Caitlin to really talk about and show some images from some in vivo imaging of actinium dotatate in AR42J variant mice, and then a quantitative comparison of actinium and lutetium data. All right, just very briefly to orient everybody, we're talking about this BioNTech system here, the gamma eye, and it's loaded for this work with a high energy, high sensitivity collimator that should be suitable for actinium. This is a tungsten collimator that is better equipped, just like in the clinical space, to handle the high energy photons that are emitted particularly from the francium and bismuth daughters of actinium. So here, just again, a little background reference. I think I'm assuming most folks are, if not all, are quite familiar with this decay chain. But for reference, we'll be looking at the 218 peak from francium and the 440 peak from bismuth, but also, if you're thinking clinically and in humans, that's with the actinium work being done, that's where we want to look. Here, we're talking about mice, and so we have the advantage of also being able to look at the lower energy, sort of 80 keV peak that is comprised of a number of emissions of gamma characteristic X-rays from a few points in this decay chain. And that's going to be really helpful for us because the mouse is small enough that these photons can escape tissue and reach the detector. Okay, so for this section of the talk, we have just a few things that we'll highlight briefly. So we're going to touch on an assessment of the spectra, which can be noisy with actinium, and then some of the flood corrections that were done once those settings were put in place. Just look briefly at, after that flood correction, how is the response of the detector across its spatial extent? Discuss a linearity and then dynamic range assessment. And this linearity calibration was also used for determining a quantification factor for the downstream in vivo imaging. And then finally, before we get to actual animal imaging, we wanted to do some mouse phantom imaging just to as a sanity check for some of those calibrations, make sure we're seeing distributions that we expect and values. It's one of those. A lot of this is prerequisite work that's well, interesting, but also has to be done, because if we see results that are confounding with a mouse phantom, we don't want to go to that, put in that energy to look at the in vivo animal imaging. All right, so starting with the spectral assessment, and this was done primarily by adjusting the high voltage on the system with a small amount of actinium placed in front of the detector, both with and without the collimator. So just to orient everybody here, each column represents a different high voltage gain setting. Each row we have two rows. One is with the collimator in place, the other is without the collimator. So here we're looking at this was a combination of a qualitative and quantitative assessment, and all of this work was done in careful collaboration with the imaging scientists at BioNTech, who of course know the system best, to understand what we were seeing in the distributions. You can see these yellow arrows might not show up the best, but should be clear. We have a 218 and 440 keV peak visible here. So this setting was selected for those windows. And then especially visible without the collimator, we have a nice peak here at 82 keV. And so this setting was selected for that peak. So when we're acquiring the data moving forward, we are typically, depending on if we want to look at 82 keV or 218 and 440 keV, acquiring the data with different system settings. So once we selected those settings and could focus on those items, just a standard flood image was collected for correction of detector non-uniformities and to help address scatter from the collimators. And we picked the following energy windows summarized in this table for the imaging. We have that 82 keV peak we mentioned. Here we're using a window width of plus or minus 20%, and did include a triple energy window scatter correction with windows centered at 50 and 140 keV. Those are plus or minus 30%. And then we have those two gamma peaks at 218 and 440 keV with a width of plus or minus 10%. For now, no triple energy window scatter correction there, although this is something that may or probably will be just explored in the future. There's So early days, there's a lot of development work that we can do here. So with those decisions made and that calibration in place, we looked at just a response across the spatial extent of the detector. So this was a 1 ml vial with 1 microcurie or 37 kBqs of activity in it that was placed at 4 different locations across the extent of the detector. So this is actually 4 separate acquisitions that are being shown side by side. And what you're seeing here is an image of the 82 keV data without and with the scatter correction. And these results looked very reasonable. We see a consistent pattern of activity on the detector. We observed consistent counts per minute, both with and without the scatter correction. And then the scatter correction, we see a reduced amount of background outside the vial, indicating that we're seeing the expected behavior, lower counts. Everything here seems sensible and reasonable. When we look similarly at the 218 and 440 keV data, we see, again, for 218, similar behavior, consistent behavior across the extent of the detector, a little more background, probably due to both a combination of scatter and septal penetration. And then, not surprisingly, even more of those effects as we move to those very high energy photons at 440 keV. Consistent counts observed across the extent of this 15-minute imaging time for each position and of both the energy windows. Okay, so this is kind of a progression, right? Like at each step, we say, okay, this seems reasonable. We move on to the next step. So here now, instead of using a single activity concentration, we are looking at still 1 ml vials, but now with concentrations varying from 0.01 microcurie per ml up to 4.64 microcuries per ml, which is close to the total amount of activity that we're going to administer later on in the image, the mouse image data that are shown. So once again, we're starting with the 82 keV peak that's at the top row, the 82 keV with the triple energy window scatter correction on the bottom row. And we see estimates of the counts per minute. We'll have a graph of this in a couple slides because it can be kind of maybe hard to do those linear relationships by eye. But we do see a linear response, quite a bit of scatter from this 5 microcurie vial that can impact the vials nearby. So those were excluded in the curve assessment that was done later on. But we see, I think, a reasonable response, clearly visible vial at 0.4 microcurie per ml. Without scatter correction, it's still there, certainly quantifiably there at 0.14, a little more in the noise, 0.01. So this also is now giving us a sense of sort of, I think, a dedicated experiment to look at the lower limit of quantitation, which is on the docket but hasn't been done here, would be appropriate. But this starts to give us that understanding of, okay, what are we going to be able to see? What won't we be able to see? Starts to set those expectations, which can be hammered out in later experiments. Similar, so here's the same data. The vials are in a slightly different ordering here, but we have for the 218 keV peak. So this is just 218 shown with at 2 levels of essentially just imaging contrast. So just different color scales. Again, those same vials, a little more challenging to discern the 0.4 microcurie vial, although it's there, 0.14 and difficult to observe 0.01, almost lost completely in the scatter in the background from this very bright vial. And then the same story, even amplified a little further with the 440 keV on bismuth 213. So again, this is helping to set kind of what are going to be our expectations as we move into the in vivo animal imaging. Now, when we look quantitatively, we do see a nice linear relationship down to that 0.14 microcurie level here up to 5. You can see focusing on these 5 vials. And on the gray dotted curve, which is that 82 keV peak, we see a nice linear relationship, which we could use to set a calibration factor for the imaging. Lower slopes on these curves for successively the 218 keV peak and then to the 440 keV peak, but we could use each of these curves to at least get a calibration factor to start with the for the analysis. And as a final step, we wanted to look at this mouse phantom, and we focused on activity in the bladder, in the kidneys, and in the tumor, with an attempt to use what we felt would be realistic amounts of activity to see how well we could recover those. So spending a little time on this slide, the kidneys were loaded with 0.6 microcurie and 1 microcurie respectively. The tumor with 0.43 microcuries of activity, and the bladder with 0.3. As you might recall from the previous slide, but they're labeled here, the bladder, you have the 2 kidneys and the tumor clearly visible, even more clearly visible with the scatter correction. Again, this is the 82 keV data. And I think we see a very nice concordance here between the activity in each compartment and the activity estimated, in fact, in both cases. This was a 30-minute scan. But if we look, for example, just comparing by eye, 0.6 and 0.7, 1.03, combined 1.9, 0.46 to 0.43, and 0.38 to 0.3. So this was an encouraging result, because this is both the shape and geometry and sort of what's roughly the expected values for our in vivo experiments. If we then look similarly at the francium and the bismuth, and this is, I think, a case of but not uncommon in nuclear medicine imaging. We have some noisy images. The quantitation is still reasonable. I would argue a couple things to note. So we still see the rank ordering very similar to what we would expect given the known activities. Clearly, we have noise, and this is a nice little word of caution in terms of things like if we're going to do xenograph tumor imaging, thinking about where that tumor placement should be relative to some other potential areas of high uptake in the images, in the animals. Another observation, which just kind of teeing up what we might see later on, we see that kind of strong correlation between the known activities in each of these compartments with the estimated activity, but we're underestimating the activity in both cases, and underestimating a little more in the 440 keV compared to the 218 keV, which was then underestimated going back compared to the 82 keV, which was also reflected in the linear responses that we see here in the resulting calibration factors. So it's one of these things where this all seemed, from a quantitation standpoint, relatively internally consistent, but might be something that, as continue to work to understand the capabilities and limitations for these 218 and 440 keV photons, that might be something we want to revisit in future experiments and calibration and characterization work to see if we can increase the agreement across all of those different peaks and potentially improve that quantitation. So just summarizing this work, The collimator definitely enabled delineation of each of these peaks given the appropriate system settings. We observed a consistent and uniform activity response across the detector for all those energy windows. We did see a linear response across a range of evaluated activity levels, really from that 0.14 vial up to almost 5 microcuries per ml. The mouse phantom imaging produced good results, particularly when imaging that 82 keV peak with scatter correction. I'd say the other two peaks look encouraging, but we can do a little more work there. So reflected here, it's possible, but more challenging. And, you know, as ever, these are early days and additional development, testing, and characterization are needed. That's probably an evergreen statement, but it's true here as well. So with that, I'll hand it over to Caitlin to dive into the in vivo experiments. Thanks.
Thanks, Jacob. So after we had completed the system characterization, the next step was to put some actinium in live mice and do a study in vivo. So this is a quick summary of the study design. It's a pretty straightforward study. We used 3 mice in this cohort that received 1 microgram mass dose and 5 microcuries of actinium labeled dotatate. These mice, as Jacob mentioned earlier, were AR42J tumor bearing. And these mice were imaged 1 hour, 4 hours, and then 96 hours post-injection. So this is the first set of images. We're showing sort of all 3 mice for every peak of actinium, just to give you a complete idea of the data and images that we got. So this is the 82 keV peak, 1 hour post-injection imaging with the same scatter corrections that we were seeing in the system characterization portion. So the uptake in the tumor at 1 hour is, we're starting to see some signal there. The right shoulder has the tumor, where Jacob's pointing right now with the pointer. We also saw some bladder present at 1 hour, especially in that mouse 1, and then some signal in the kidney area a little bit below the tumor. Then now at 4 hours, still 82 keV, we're seeing a bit more uptake in the tumors, a bit more concentrated activity there. The bladder has kind of disappeared. We're not seeing so much bladder signal, and a little bit more in the kidneys again. Now at 96 hours, there's some washout seen. We're still seeing pretty high signal in the tumors in all 3 mice, which is super promising, 96 hours post-administration, and also some signal in the kidney region. So those 82 keV images looked the best, which is sort of what we expected, but we still, based off of the system characterization, we still wanted to look at 218 and 440 images, obviously. So here is a 1 hour post-administration for both 218 on the left and 440 on the right. We are seeing, as expected, a bit more scatter here, especially in that first mouse that had high bladder. We saw in the 82 image as well. There's a lot more scatter throughout the body here, definitely impacting some of the organs we're seeing, but we are seeing a little bit of signal around the tumor, arguably maybe some around the kidney in some of these images. Now at 4 hours post-injection, a lot of that bladder signal has cleared, so there's a lot less scatter present. We're seeing, especially in the 218 images, some tumor uptake that is a bit more concentrated than we saw at 1 hour. Definitely less than the 82 keV images though still, and some scatter throughout the body, some around the area of the kidneys, and just sort of throughout the abdomen. And then at 96 hours, seeing a lot of clearance from 4 hours. Not so much tumor signal, except we are seeing in that second mouse, there's still some tumor signal that's pretty discernible, which is very promising, 96 hours post-injection in a 218 keV image. So now we're going to look a bit at some organ ROIs that were drawn around the kidneys and also the tumor from those images we just looked at. So going from left to right, we have 82 keV, 218 keV, and 440 keV % ID graphs for the kidneys and the tumor. So the kidneys here across all three isotopes, or three peak settings, were pretty low, consistently around 1, maybe some up to 2%, especially in the 218 and 440 keV images at 1 hour. But the tumor uptake and % ID tracked pretty well. So in 82 keV, 1 hour post-injection, there was some signal, about 3% ID. Then it goes higher by 4 hours to right around 4.5% ID, and washing out down to, again, about 2% ID in the 82 keV images. And then the same similar trend was seen in the 218 and the 440 keV images, comparing those two to each other, where there was highest % ID at 1 hour, likely due to some of that scatter that we were seeing. Then washing out 4 hours and 96 hours for both 218 and 440 keV tumor uptake. So once we'd completed that initial actinium study, we wanted to compare it to something. So we performed a lutetium labeled dotatate study to be able to compare our actinium data to lutetium data on the gamma eye. So we did perform, of course, some system characterization for lutetium to be able to do this. We're not going to go super in depth into that here because it's not really the focus of this talk, but we performed a flood phantom correction and also 8 vial activity curves that were used to determine linearity and also to determine the calibration factor for the system. And we performed this on both the medium energy general purpose collimator, MEG-P, which is typically used for lutetium imaging, and also on the high energy, high sensitivity collimator, mainly so that we would be able to image lutetium on that same collimator to then compare data to actinium and keep the system parameters as close as possible. So this study design was a bit more complicated, so I'm going to describe it for you. So in this first cohort, this first cohort has been completed. We had lutetium labeled dotatate that was injected into 3 mice that received 1 microgram and 100 microcuries of activity. We wanted to use higher than typically administered activity for this to kind of maximize the signal. And these mice were injected and then imaged on the gamma eye 4 hours post-injection. That imaging lasted 30 minutes, which matched up with the typical imaging period of time we use for each peak setting for actinium. And then these animals were sacrificed immediately following the 4-hour time point collection. And we then performed a bio-D on the tumor and kidneys. So we collected those organs and then gathered their weights and also ran them on a gamma counter to be able to compare biodistribution data from the same mice to imaging data ROIs. And then we also planned to do this similar study with actinium labeled dotatate. We have not been able to do that yet purely due to actinium availability limitations, which I'm sure a lot of people are familiar with, has been a global phenomenon, especially this summer. So we're still waiting to perform this second portion of this study, but I'll still describe it because it'll put into context why the lutetium study was performed the way it was. So theoretically, we will administer 1 microgram of actinium labeled dotatate with a high level of activity. We will then image them 4 hours post-injection, just like with lutetium cohort. We'll sacrifice those animals after the 4-hour time point. And then we will wait a few days for the carcasses to reach secular equilibrium between the actinium daughter decay chain. And then we will image the carcasses again after they've reached secular equilibrium. Following that second imaging session, we will then perform a bio-D and gather the tumor and kidney weights and also run them through a gamma counter. So we'll be able to compare actinium-labeled dotatate biodistribution data to pre- and post-secular equilibrium data, and then also compare all of that to lutetium dotatate. So getting into the lutetium dotatate mice that we were able to perform this study on so far, these are the images that we gathered. 30-minute imaging session yielded a very clear tumor uptake in all 3 mice and also very clear kidney signal in that kidney region. So here are some organ or ROI data for the gamma I portion of this analysis, and then bio-D data comes from gamma counting those organs as described earlier. So we can see in blue gamma I data, percent ID per gram on the left graph and percent ID on the right graph, and then bio-D in red on both graphs. So the kidney and tumor percent ID per gram and percent IDs are very consistent between the 2 methods of analysis. So that was super promising for the gamma I as a tool to accurately assess lutetium imaging, lutetium organ activity levels. But what we really want to care about right now is comparing lutetium to actinium. So in the next slide, we can look at percent ID. In the red here, so in the pink is lutetium bio-D data. In the red, the bright red is lutetium imaging data. And then the blue charts, the blue peaks are the actinium data that we looked at in the previous study shown right before this lutetium study was introduced, the 82, 218, and 440 keV peaks. So the kidney levels are all very similar, very low. The tumor levels for percent ID for the actinium are a little bit lower than the lutetium. But if we look at the next slide, once we look at percent ID per gram, correct for the difference in tumor size that we note in the bottom corner, there was a higher tumor volume, average tumor volume for the lutetium cohort than for the actinium cohort. So once you take that into account and look at percent ID per gram, then we can see that the lutetium data is for imaging and bio-D is very comparable to at least the actinium 82 keV peak, which is super promising to see how close those values are. The tumor 218 and 440 keV peaks are a little bit lower, and that is in both the kidneys and the tumor, and that is consistent with what we saw in the mouse phantom and in the activity curve linearity that Jacob mentioned earlier, that those seem to be underestimating the activity present. So we're seeing that same pattern here again, which is promising that at least we're consistently seeing the same underestimation for those settings, and that there's further optimization that we need to do for those 2 peaks. So some conclusions and future work. The gamma I system was successfully calibrated and characterized to enable in vivo actinium-225 imaging in mice. In vivo actinium-225 dotatate imaging was successful up to that 96 hours post-administration using a practical administered activity of 5 microcuries and practical imaging times of 30 minutes. The organ actinium dotatate uptake in the tumor and kidneys was consistent with the lutetium dotatate uptake that we saw for the 82 keV peak especially. Some future work is completing the second portion of that lutetium study, where we will have in vivo imaging, imaging at secular equilibrium, and then a biodistribution with actinium-labeled dotatate. And that will be performed with higher administered activity than we used in the study already completed. We'll then be able to compare the results and performance to the lutetium dotatate data, as well as to that lower administered activity actinium dotatate data. And then finally, we will continue optimization of those 218 and 440 keV imaging settings, probably be a lot of continued optimization. Some acknowledgements quickly. We'd like to thank Eric Fenn from Ratio and Maria from BioMTech, who were very helpful in data analysis and presentation for the webinar. The team at BioMTech who's been collaborating and helping guide system characterization and these initial actinium studies on the gamma eye, as well as the biology team at Ratio for assisting with a lot of mouse care, the radiochemistry team for helping prepare compounds and activity for these studies, and the data team at Ratio for collaborating in data analysis and enabling data entry for these studies. So thank you all. I think we're going to get into the Q&A section now.
Thank you, Dr. McCutcheon and Dr. Hesteman, for the insightful presentation. So now we'll give everyone an opportunity to submit a couple of questions through the Q&A section. And I'll go ahead and review some of the questions that initially have come in. So first question, how would you quantify daughter redistribution?
I can jump on that one. So it's an interesting topic that I think will need a little more investigation. So the idea being, if upon the decay of the actinium, we have the daughter radionuclides are no longer bound, then you could have non-equilibrium bismuth in particular potentially redistribute to other tissues. One approach here is to use the 218 keV peak, making an assumption that the francium is decaying in the location of the actinium, and then the 440 keV peak, and assume that the bismuth may potentially have redistributed, for example, to the kidney, so that you would see a higher signal there. So you can compare those signals. This could potentially also be done using that 82 keV peak, but likely we would need to dig in a little more into exactly kind of which decays are contributing to that 82 keV peak, and what would we expect. Need to model that out a little bit in terms of what you might expect if there is redistribution in terms of the relative signal intensities of those two peaks, of values from those two peaks. And I think that having some data with a higher administered activity and or longer imaging acquisition times, looking in vivo and ex vivo at those data once you've reached equilibrium, could be really informative to assessing the feasibility of quantifying that kind of redistribution.
Perfect. Thank you for that answer. We have another question regarding, it says the poor resolution of images. Is this related to the actinium decay chain and the emitted daughters, or is this a result of the instrument itself?
So you have a few factors that are coming into play. And I actually thought the images looked quite good, especially at 82 keV, and even that some of the 218 keV images looked excellent, like that 96-hour image of mouse 2. So you have typically relatively low administered activities and relatively low abundance. So your images are going to improve with counts, because we have Poisson statistics here. So the more counts, the better your images will look. So we're relatively count starved. And then for those higher energies, you are going to have increased scatter, increased septal penetration. There are just a number of factors that are at play here. So I think this is why alpha imaging is imaging of alphas, especially for actinium-225, is challenging to begin with. I thought these images look actually quite good. And then as we continue to, or as the BioNTech team continues to kind of look at these results, work on the collimator, and/or continued optimization of scatter correction at higher energy peaks or corrections on that front, these images will only improve. It's a tricky imaging problem, though.
Thank you for that very insightful answer. Another question, which software was used to view and analyze the images?
Oh, so a combination of, there's a software that comes with the imaging system that was used for some of the analysis. And then here we were using vivo to do some continued analysis and visualization. So it was a combination of the analysis software that came with the imaging system and the vivo software.
Great, thank you. I believe that's the end of the submitted questions. We can give everyone just about another minute if anyone has any last minute questions they'd like to submit. If not, we'll go ahead and end our session a little early today. It looks as if everyone has had a chance to submit their questions. So I'd like to thank Dr. McCutcheon and Dr. Hesseman for the presentation today, as well as for taking the time to address many of these questions. I trust that we've been able to provide you with some relevant information to the studies that you're conducting back into your own lab. As I mentioned at the start of the webinar, we will be sure to answer any outstanding questions in the written transcript and work to get this out to you over the next few days. And if in the days and weeks to come you have any further questions about the work that was presented today or questions about any of the equipment shown, particularly the Gamma Eye, I encourage you to reach out to us here at Syntica, and we would be happy to discuss further. We'd welcome the opportunity to discuss your specific research goals and how any of our equipment can help you move forward. Thank you all again today for your time to attend the session. We look forward to seeing you at a future Syntica event, and I hope you all have a great day. Thank you again, Dr. Esterman and Dr. McCutcheon.
Thank you.
Thank you.